increasing and decreasing on functions, and the first derivative test. All right, so let's assume f is a continuous function on a closed interval and differentiable on an open interval from a to b. If f prime is greater than 0 on the open interval, then we say f is increasing on the closed interval. So let me draw you a little picture here. And let's say we have a function that goes something like this. So we're going to call this, let's see, I'll call this, yeah, I'll just go with a and b. All right, so if you think about between a and b here, so right here at a, the derivative is equal to 0. Similarly, right here at b, derivative is 0. Everywhere between a and b, the slope of the tangent line is a negative number. Therefore, the derivative is negative. So because the derivative is negative on this entire interval from a all the way to b, you see that the function is actually decreasing. It is falling. So we would say that this function is decreasing on the closed interval from a to b. Note that we include the endpoints. So even though the derivative at a is 0 and the derivative at b is 0, by the definition, we're going to say that the function is decreasing on the interval from a to b. This function would be increasing on the interval from negative infinity all the way up to a. So it's increasing this entire time. Now we never include infinity, so we're going to use parentheses there, but I would include the a. And then also note that this function is going up, increasing, where the derivative is positive over here on the interval from b to infinity. So we're going to include the endpoints when giving intervals of increase and decrease, as long as the function is defined there. Now, if you break up a function into intervals of increase and decrease, if you can determine that, then you can locate relative maximums and relative minimums, because obviously if a function changes from increasing to decreasing, that's going to create a relative maximum. And if a function changes from decreasing to increasing, that's going to create a relative minimum. So what we can do is we can use the derivative to figure out where's the derivative positive and where's the derivative negative. And then if we can figure out where those transitions happen, we can locate the positions of relative maximums and minimums in that way. So we're going to start, actually we're going to jump right in. We're going to find the intervals over which a function is increasing and decreasing, and then I'm going to show you the method for using a number line to determine where we have local extrema. So here's the method. I'm going to start by finding the critical points. Remember that those are the places where the derivative is either equal to 0 or the derivative is undefined. So f prime, in this case, is 3x squared minus 3x. This will never be undefined, but it could potentially equal 0. Let's work out where that happens. Factor out of 3x, x minus 1 is equal to 0, and you see that we end up with two critical points, 0 and 1. So now what I'm going to do with those critical points is I'm going to plot them on a number line. Now, I'm going to look at values of the derivative in the intervals created by plotting these. So we have this interval that goes from 1 to infinity. We have an interval from 0 to 1, and we have an interval from negative infinity to 0. Now I'm going to denote the fact that the derivative is actually equal to 0 in those two places by putting a 0 there. And now what I'm going to do is I'm just going to choose a test point in each one of these intervals. One in here greater than 1, one between 0 and 1, and one less than 0. So I'm just going to pick a point. So let's choose a number greater than 1. How about 2? What is f prime of 2? So I'm just randomly choosing a point in each one of these three intervals. So the easiest way to do this, by the way, when you're trying to evaluate is use the factored form of the derivative. So what's f prime of 2? Well, it's going to be 6 times 1. Now, I don't really care what it is. I only care that it's positive. Remember that a positive derivative tells me that my function is increasing. So I now know that when I choose a number greater than 1, I get a positive derivative, and I'll denote that that means it's increasing by putting an arrow right there. Let's choose a number in between 0 and 1. How about 1/2? Let's see. So what is, try that again. What is f prime of 1/2? Well, once again, using that highlighted derivative, that's going to be 3/2 times negative 1/2. Once again, I don't actually care what it is. I just care is it positive or negative. In this case, negative. A negative derivative tells me my function is decreasing. And then finally, I'm going to choose a value less than 0. How about negative 1? So what am I going to get when I plug negative 1 into the derivative? Once again, using the highlighted version, negative 3 times negative 2, that's going to be positive. Denote that with a plus and an arrow up above. So what this tells me is that my derivative changes from plus to minus to plus. It tells me that my function is going to increase, then decrease, then increase. So looking at this number line, I get a couple things. First of all, I can see exactly where the intervals of increase and decrease are. I can also see where my relative extrema are. All right, so first I'm going to give the intervals of increase. This function is increasing whenever x is in the interval from negative infinity up to 0. We never include infinity, but we will include the endpoint of 0. And also on the interval from 1 to infinity. So increasing here less than 0 and increasing here greater than 1. My function is decreasing when x is between 0 and 1. And now where do we have local extrema? Well, you can see that at 0, the derivative changes from positive to negative. The function goes from increasing to decreasing. That is a relative maximum at x equals 0. And I'm going to have a relative minimum at x equals 1. Now, why do I have a relative minimum at 1? You see the function changes from decreasing to increasing. Derivative changes from negative to positive. Now, one last thing here. Note the requirement to justify your answer. When it comes to justifying maximums and minimums, you must state the following. I know there's a maximum at 0 because the derivative changes from positive to negative at 0. So since f prime changes from positive to negative at x equals 0. That is the exact wording you need to use. How do I know there's a minimum at 1? Because f prime changes from negative to positive at x equals 1. Now, if it doesn't say to justify, you don't need to write those parts. You just have to give the answer. But when it says justify, and this is something they ask on the AP test, justifying a maximum or a minimum, that's what you have to write. The derivative changes from positive to negative to justify a maximum. Derivative changes from negative to positive to justify a minimum. All right. Determine the local extrema for the function y equals 1 over x squared. All right, same process. I'm going to start by finding the derivative. And to find this derivative, I think what I'll do is I'll write it as x to the negative 2. That makes y prime equal to negative 2x to the negative 3, or negative 2 over x cubed. So I'm going to start by finding the critical points. Now, this derivative will never equal 0 because the numerator is 2, can't ever equal 0. But it can be undefined. So y prime is undefined, when x cubed is equal to 0, which is the same as x is equal to 0. So we'll have division by 0. So number line, I'm going to plot 0 there. We're going to look at values of the derivative, just like I did up above. But this time where I put zeros above those values, I'm not going to put a 0 because the derivative is not 0 there. It's actually undefined. So I'm going to notate that. I'm going to attempt to notate that. There we go. All right, now choose a value greater than 0. How about 1? When I plug 1 into this derivative, I'm going to get -2, negative, and that tells me that the graph of y is going to decrease because the derivative is negative. Choose a value less than 0. How about -1? That's going to result in a +2. Derivative is positive. Function is increasing. So my function changes from increasing to decreasing at 0. So that leads me to believe that I have a maximum at 0, but actually I don't. And the reason I don't is because look what happens. Look what happens if you try to plug 0 into this function. You don't get an answer. Technically, in this case, 0 is not actually a critical point because it's not even a point on the graph. Up above here, that was not a problem. I could plug 0 in here and get an answer. I could plug 1 in here and get an answer. They are included in my intervals of increase and decrease. They are maximums and minimums because the function exists there. This one, and that's why it's important to denote this as non-existent, because that reminds me to check this. I don't actually have a maximum at 0. I don't have anything at 0 because I don't even have a point at 0. And since that's the only possible maximum or minimum, this function has no extrema. And that's a very special case. You might look at this and realize that there's actually a vertical asymptote at 0 if you were to look at the graph. If you were to look at the graph of this function, what you'd see is something that looks like this. It increases on the left and decreases on the right. No maximum and no minimum. All right, now, what if we're on a closed interval? So if I come back up here to the notes here, what the first derivative test, all right, that's what I've been doing. This is what we call the first derivative test. You determine the intervals of increase or decrease using a number line. That's what I did right here. Wherever the derivative changes from positive to negative, you have a local maximum. If the derivative changes from negative to positive, you have a local minimum. If you are asked to get the actual y value, so remember that the x value is not, the x value is the location of the maximum. It is not the maximum value. You have to substitute back in the original function. So for instance, in this problem right here, I know I have a maximum at 0. If I really wanted to get what that maximum value is, I would plug 0 into here. And then the last point here is if your function's on a closed interval, don't forget to check the endpoints. And that's because you recall from previous lessons that we, on a closed interval, the endpoints themselves will represent maximums and minimums. So here I want to find an absolute maximum or an absolute minimum. So when I do this, I can do the same process that I did up above, except now I'm going to have endpoints. I have to consider those as well. So I want to find absolute maximum and absolute minimum. So once again, I'm going to start by taking the derivative. 12x cubed minus 24x squared. This will never be undefined, but it will equal 0. So set that equal to 0. I can factor out a 12x squared, which will leave behind an x minus 2. Yep. Setting that equal to 0, resulting in two different x values, 0 and 2. So I'm going to plot that on my number line. So, well, actually, I don't have my number line doesn't go on here because we actually have endpoints. So we're really only going from -2 to 2. So 2 is one of those critical points, but 0 is also a critical point. So I'm going to denote each one of those. So I don't have to check beyond 2 because I'm not actually interested in what's going on beyond 2, and I don't have to check less than -2, but I do have to check in the interval from -2 to 0 and from 0 to 2. So let's choose some test points here. Let's look at f prime at 1. Remember, I'm going to look at the value of f prime to get the behavior of f. So f prime at 1 is going to work out to be, and once again, I'm going to use the factored form of the derivative. That's the easiest way to do it. 12 times -1, which is -12. That's negative. Function decreases. And then let's choose a number between -2 and 0. How about -1? When I plug in -1, I'm going to get still a positive 12 and then times a -3, -36. Ooh, that is also negative. So now note that at the critical point 0, the derivative does not change sign. Thus, I do not have a local maximum or a local minimum. If you look at the general trend here, you might see that the function decreases, derivative goes to 0, and then it decreases some more. So it's pretty obvious here that the absolute maximum is going to be at -2, and the absolute minimum is going to be at 2. So I'm going to have an absolute max at x equals 2, -2, and an absolute minimum at x equals 2. Now, let me show you one other thing here, because when you have a continuous function on a closed interval, you might recall we have a theorem from last time called the extreme value theorem that guarantees I will have an absolute max and I will have an absolute minimum. So when you're on a closed interval and you have a continuous function, you can use, so this is an alternative. This is a great answer and we're done, but this is an alternative way. You can use what's known as a candidates test. And what a candidates test means is you find your critical points. So we know we have critical points of 0 and 2. You take your endpoints, and this is much like what we did when we first introduced maximums and minimums. We have endpoints of -2 and 2. And what we'll do is we'll just evaluate the function at each one of those. So the candidates for absolute max and absolute minimum are always critical points and endpoints. Those are always the places where you can have a maximum or a minimum. So this is an alternative way if I'm looking for an absolute max and an absolute minimum, is take your critical points and your endpoints. We don't need to do 2 twice. Plug them into the function, because we want the y value. What do you get? Well, when you plug 0 in, you get 0. When you plug 2 in, you're going to get 3 times 16 minus 8 times 8. 48 minus 64, -16. I think that's what that is. And then when I plug -2 in, I'm going to get 3 times 16 minus 8 times -8, which is 48 plus 64, which is 112. And now, if you look at these values, the greatest of them is the absolute max. So that's this. And the least of these values is the absolute minimum. And you can see that fits with exactly what we had before. Absolute max when x is -2, right there. And absolute minimum when x is equal to 2. So you can use either one of these methods. This candidates test idea only works when you have a function on a closed interval. It doesn't work when you're on an open interval, which is why I didn't use it on either one of these two up here.